Our second lesson for oscillatory motion regarding simple harmonic motion is for springs. So we looked at pendulums, and springs are very closely related. So what we're seeing here is a tire gauge, a tire pressure gauge, and it uses a spring to tell what the pressure of air is within the tire itself. Okay, so what they are talking about here, it says the force required to stretch or compress a spring is directly related to the stiffness of the spring, which is represented by the spring constant K. And it is also the amount that the spring is stretched or compressed. So how hard you have to press to compress a spring depends on how far you want to compress it. If you just want to compress it a little bit, it takes a little bit of force. If you want to compress it a lot, it takes a lot of force. Same thing if we were to stretch a spring. To stretch it a little bit takes a little bit of energy or force. If we want to stretch it a lot, we would have to apply a lot of force. Again, it is also related to how stiff the spring is. So if you compared the spring within your pen, like a clicky pen, or a spring on a trampoline, they would have a different spring constant because it requires different amounts of force to stretch them. All right. So this force supplied by a spring, an elastic band, something that's stretchy is what we're looking at here, can be calculated using a relationship called Hooke's law. And Hooke's law is the force of a spring is equal to the negative K, which is our spring constant, times X, which is the amount the spring is compressed or stretched. Now notice that X is a vector, so we do need to consider whether it's a positive or negative stretch, okay? Now this negative here, it says, the negative sign is there to remind us that the spring force is always a restoring force. So it will always be in opposition to the direction of stretch, where the force will be. Again, spring constant K is how stiff something is. If it has a large spring constant, it means it is harder to stretch or compress. So large K, harder to stretch or compress. And again, it doesn't necessarily have to be a spring. We could be talking about like a bungee cord or an elastic here. Obviously, those don't compress as well, but we could measure their stretch. All right, example 1, in a tire pressure gauge, the air in the tire pushes against a spring when the gauge is attached to the tire valve as shown in the figure above. That was the first picture we looked at. If the spring constant is 320 newtons per meter, that's the unit of K, and the bar indicator extends 2 centimeters, what force does the air in the tire apply to the spring? So we're looking at F of S is equal to negative KX. So it doesn't say whether this was a positive or a negative. So I would assume if we'd drawn it as in the picture, it has moved outwards or to the right by 2 centimeters. Therefore, we are going to input that as a positive value. All right, K was 320 newtons per meter. X is positive 2 centimeters. We need to change that into meters. So 0.020 meters. Oh, and I forgot my negative at the front there. When we calculate this out, we get negative 6.4 newtons. Example 2, when a 2.45 kilogram mass is vertically hung from a spring, the spring stretches by 12.4 centimeters. What is the spring constant in the spring? So what I'll do is draw a little diagram for us first. When we see a spring, it would have a normal resting length or compression. If we are hanging something from a spring, it is stretched in this case. So it says it is stretched by 12.4 centimeters. All right. So we're going to include a little bit of a free body diagram here. So our mass is attached and the mass has gravity acting on it. It also has a spring force acting on it in an upwards direction. These forces are equal and opposite. So I can say that the absolute value of the force of the spring is equal to the absolute value of F of G. So the absolute value of negative Kx is equal to the absolute value of M times G. All right, so the absolute value of negative K is what we're looking for here. X, because it has stretched 12.4 centimeters down, X is negative 12.4 centimeters. This is equal to the absolute value of the mass, so 2.45 kilograms times gravity, negative 9.81 meters per second squared. All right, when I solve this, again, the absolute values just mean forget about the negatives. Everything has a positive value. K is equal to 194 newtons per meter. Again, the unit newtons per meter is what we represent K with. Again, it has to be an absolute value here because F of S is upwards and F of G is downwards. So because they have opposite directions, we would have gotten negatives. Therefore, we needed to use our absolute values. All right, the period of vibration. So if we were to stretch a spring and let it go, it will vibrate up and down or side to side, depending on which way we've stretched it. And so we can represent this equation, that idea with an equation. This is the ideal spring equation, and it is on your formula sheet as well. Where T is the period in seconds, M is the mass of the weight in kilograms, the spring constant is K. And so for an ideal spring, the spring is considered to have a mass of 0. Okay, so then the period of vibration doesn't require gravity or an amplitude of vibration. What they're saying with this mass of 0 is that the spring's mass is not included in the mass of what's on the spring. Okay, and again, G is not involved and neither is the amplitude or how far it stretches in either direction. So what is the period of a vibrating spring with a spring constant of 100 newtons per meter if a mass of 500 grams is hung from the spring? So we're going to use this formula, T equals 2 pi times the square root of M over K. Again, be aware of what you're square rooting. So we want to input these two numbers and divide them out and then square root and multiply by 2 pi. Okay, just order of operations in our calculator is going to be important. So this is 2 pi. The mass is 500 grams, so we change that to kilograms. And divide by 100 newtons per meter. When we multiply this all out, we get 0.444 seconds as the period.